Lesson 6 is solving exponential equations, and in 6.1 we're going to be solving exponential equations that have like the same base on each of the exponentials. So starting in the upper left, if the bases of an exponential equation are the same and are not equal to 1, 0, or -1, that would be kind of like a weird special case, then the exponents must equal each other. So if the bases are the same, the exponents must also be the same value in order to keep the equation balanced. So example 1, we're going to solve both of these equations. For 1a, it's 5 raised to the x power equals 5 raised to the 2x minus 4. So you can see like both the bases, that's like kind of the bigger number that's like below the exponent, both the bases are the same. They're 5 and 5. So if both the bases are the same, then in order for the equation to be true, meaning each side actually does equal each other, then the exponents have to equal each other. So to figure out what x makes that work, we just have to set the exponents equal to each other. So we would do x equals 2x minus 4. And then now we just need to solve for x. So we just have a linear equation. So we just need to get the x's on the same side of the equation. I'm going to cancel out that 2x since there's already that like -4 over there. So in order to cancel out the 2x, I would subtract 2x from both sides. And then this is like 1x minus 2x. So 1 minus 2 would be -1x, or just -x. And then the like 2x minus 2x cancels out. I bring down the -4, the -4. And then I have -x equals -4. And when we're solving for x, we just want like positive x. We want the coefficient to be +1. So in order to change the -x to a positive x, we would either multiply or divide both sides by -1. So the -x divided by -1 would turn into a positive x, and then -4 divided by -1 would turn into +4. So it'd be x equals 4. And then moving on to b, so 2 raised to the 9x minus 6 equals 2 raised to the 5x minus 3. So again, we have the same exact base here. So in order for the equation to be a true statement, that means if the bases are the same, the exponents will also have to be the same in order to make it true. So we can take each exponent, one is 9x minus 6 and the other 5x minus 3, and just set them equal to each other and then solve for x. So 9x minus 6, and then equals the other exponent, 5x minus 3. Again, we have a linear equation, so we just want to get the like x's on the same side of the equation first. I don't want to deal with negatives, so I'm going to subtract the 5x over as opposed to the 9x. So subtract 5x from both sides. 9x minus 5x is 4x, and then I bring down the -6, and then 5x minus 5x, that cancels out, and then I bring down the -3. And then now that I have the x's on the same side, we didn't have to do this on the last problem, but my goal is to like isolate x to get it by itself. So I would want to usually undo addition or subtraction first. So that means I'm going to cancel out this -6. So I'm going to add 6 to both sides. So then I bring down my 4x. The -6 plus 6 cancels out. And then I have equals -3 plus 6, which is 3. And then my goal is still to just get x by itself. So that 4 is being multiplied by the x. So to cancel out multiplying by 4, I would divide both sides by 4. So 4 divided by 4, those wipe each other out. So we're just left with x. And then we have 3 divided by 4, but we can't really like divide it and get a whole number. So I'm just going to leave it in fraction form. So it'll be x equals 3/4. So for 6.1, those are specifically only when like the bases of the exponential are the same. If that's the case, then you can just set the exponents equal to each other to solve for x. And then moving down to 6.2, so this is like exponential equations with different bases. So up here, if the bases of an exponential equation are not the same, sometimes, not all the time, but sometimes you can rewrite the equation with matching bases. So for example 1, this is just going to be if we have to rewrite one base. So it's, I don't know why I labeled it 1a if there's only one of them, but so for example 1a, it's 2 raised to the 3x equals 128. So these bases are not the same. Like this would be like a 128 to the first power technically. So the bases are not the same, and so before we can actually like solve for x, we have to figure out a way to get them to have the same base. So 2 is like already a prime number, so we're most likely not going to change the 2. But we want to see if we can rewrite 128 as like 2 to a power, like and make 2 our base, and then that way we would have the same base. So if I like just start kind of like listing out the powers of 2, so like let's see. So 2 squared is 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32, 2 to the sixth power is 64, and then 2 to the seventh power is 128. So that means that these are like the same value, so I can take that 128 out and just replace it with 2 to the seventh power, and then we'll end up having the same base. So it'd be 2 to the 3x equals, instead of 128, I'm going to do 2 to the seventh. So from like here to here, I'm not changing the value, I'm just like rewriting the base. And then now I have the same base, both 2's. So because I have the same base, now I can go ahead and set the exponents equal to each other. So one is a 3x, one is a 7. So it'll be 3x. Oops, not 3 to the x, but 3x. And then equals 7. And then now our goal is to just get x by itself to solve for it. So the 3 is being multiplied by the x. To undo multiplying by 3, I would divide both sides by 3. And then 3 divided by 3 would cancel out. And I'd be left with x equals 7 thirds. So x equals 7 thirds. So if you start off a problem without the same base, but you can change them into the same base, that's kind of what you want to do as like the best case scenario in this case. I don't know why I'm saying that. But anyways, if you can make the bases be the same, that's what you want to do for 6.2 anytime they don't initially start off being the same. Okay, so example 2, which is when we have to rewrite both bases. So if we look at 2a, it's 1,000 to the x power equals 100. And it doesn't like really look like we would have to necessarily rewrite both bases, because you know, if we take like 100 and like multiply it by 10, it would give me 1,000. But the reason we have to rewrite both is because I can't like take 100 and raise it to an exponent to get 1,000. It would take me too far. But both of these, like 1,000 and 100, are both powers of 10. So like 10 squared is 100, and 10 to the third power is 1,000. So that means that we could rewrite them both as like a base of 10, and then we'd be able to kind of use the trick from like the previous section of setting the exponents equal. So instead of 1,000, I'm going to replace it with 10 to the third power. So it'd be 10 to the third power, and then that would be raised to the x power, because we like just swapped out the 1,000 for 10 to the third, and then that like whole thing was still being raised to the x. And then over here, instead of 10 squared, or sorry, instead of 100, I'm going to put in the 10 squared. And then before we can set the exponents equal, we just have to like make sure it's kind of simplified. So when you have a power raised to another power, you multiply those exponents. So this would be like 3 times x. So this would be 10 to the 3x, and then equals 10 squared. And then now we have like the same exact base. So we can go ahead and set the exponents equal to each other. So it'd be like 3x equals 2. So 3x equals 2, and then our goal is to like solve for x, get x by itself. So I would have to divide both sides by 3. So that 3 is being multiplied by x, and we need to cancel it out. So 3 divided by 3 cancels each other out, and then I have x equals 2 thirds, and we're just going to leave that one as a fraction as well. So x equals 2 thirds. Okay, so moving on to b, which is the last one from this section. So 49 raised to the 3x plus 1 equals 343. So for this one, you kind of always want to see if like you can rewrite one as like the same base as the other first, because that would make the problem a little bit faster. But like if I were to like try to rewrite 49, I don't know, if I were to like try to figure out what 49 squared is, it's like over 2,000. So that's not going to do me any good to like try to rewrite that. But I know for sure that like 49 is 7 squared. Like 7 squared is 49. So once you know that, you can maybe check to see like, okay, well, is 343 a power of 7? So we'll do like 7 to the third power to check to see. So 7 to the third power is 343. So it's not like something that you have to like have all these like powers, like squares and cubes, like memorize. I would say the one thing, like the main thing you'd want to know is like the squares, like knowing that 7 squared is 49. But even if you don't know that, you can just pull up like a perfect square table. And then that gives you a starting point of like trying to figure out with like the sevens, for example. So for this one, I'm going to take 7 squared and pop it in for 49. So it'd be 7 squared. And then that whole thing is still being raised to the 3x plus 1. And then I'm going to take the 7 to the third power and put it in for 343, because those are equal. And then now I have like a power raised to another power. So I would have to multiply those exponents. So think like distributing in because it's multiple terms. So this would become 7. And then 2 times 3x would be 6x. And then 2 times 1, so it'd be plus 2, equals 7 to the third power. And then if that part, like with distributing, is kind of confusing, instead of like distributing it from that step, you could just write it as like 2 times 3x plus 1, and then distribute it after if you prefer that. Both will work out the same way. Okay, so now we have the same bases, 7 and 7. So we can go ahead and set the exponents equal to each other. So 6x plus 2 and 3. So 6x plus 2. And then equals the exponent on the other side, 3. And then we're trying to solve for x, so that means get it by itself. Usually we undo the addition or subtraction first, so I'm going to cancel out that plus 2 by subtracting 2 from the other side. And then I would bring down my 6x, and then 2 minus 2 cancels out, and 3 minus 2 would be 1. And then trying to get x by itself, the 6 is being multiplied by it, so I would have to divide both sides by 6 to cancel out the multiplication. So 6 divided by 6 would cancel, and then I would be left with x equals 1/6. Okay, so moving down to 6.3, this is solving exponential equations using logarithms. So this is just like a quick little review. But exponentials and logs or logarithms are inverses of each other, so they can be used to like kind of cancel each other out. So we're going to use inverse operations to isolate x in each of these expressions. So usually like when you use inverse operations, you would do it to both sides of the equation. This is like just an expression, so I'm not worried about changing the value. I just kind of want to cancel out the exponential or cancel out the log. Okay, so for the b to the x, my goal is to isolate x. So I would have to use the inverse of an exponential, because this isn't like any, like something to an exponent is an exponential. And whatever the base of the exponential is, which in this case it's b, I would use a log with that same base to cancel it out. So I would log base b, the exponential with the base of b, and then these two together cancel each other out, and then it leaves us with just the exponent from the exponential. And then if we were to do that backwards, so like if we had log base b of x and I wanted to get the x by itself, I would have to use the inverse of a log with a base of b, which would be an exponential with a base of b. So the log of the base of b and the exponential of the base of b cancel each other out. So if I were to like exponentiate this, that means that I take b as like a base of an I would take b as a base of an exponential, and then I would raise it to the log base b of x. So that's called like exponentiate, when everything in the original line turns into an exponent. And then these two together cancel each other out, and I would just be left with the x. Okay, so if you start with an exponential, you would use a log to cancel it out, and if you start with a log, you would use an exponential to cancel it out. So example 1, solve each equation. For 1a, it's 3 times 8 raised to the x minus 5 equals 276. So before we can use, we have an exponential in this equation, like the 8 to the x minus 5. Before we can use a log to cancel it out, it has to be isolated, meaning that the exponential is by itself. So we have to get rid of this 3 that's out in front of it. I don't have to get rid of this minus 5 because it's with the exponent. I can't really get rid of it until the end. But if you have something being multiplied out in front or added after that's not a part of the exponent, those you would want to get rid of. Okay, so if we want to cancel out the 3, it's being multiplied, so I'd have to divide by 3, and then I'd have to do it on the other side as well. So the 3 divided by 3, that would cancel out, and then 276 divided by 3 is 46. So this would be 8 raised to the x minus 5 equals 46. And then I'm going to actually move this over to give me kind of room to log both sides. Okay, so I have an exponential with a base of 8, so I have to use a log with a base of 8 to cancel it out. So that would look like log with a little 8 next to it, and then whatever I do to one side of the equation, I have to do to the other. So I'll do log with a little 8 down there. So the log with the little 8 and the exponential with the base of 8 cancel each other out, and it would leave me with just the exponent part from the exponential. So x minus 5, and then the log with the base of 8, log base 8 of 46, you'd have to use a calculator for it, and a lot of times with logs, we just leave them in this form without actually putting them in. Especially because to do log base 8, you'd have to have a special calculator, and in the upcoming lessons, we're going to learn how you would be able to convert it into something that you could use with a regular calculator. But for this lesson and in this checkpoint, it just leaves it in that form. So the final step is to just go ahead and get x by itself. So I have to get rid of that minus 5 by adding both sides, or adding 5 to both sides, and I'm just going to add it to the end of the log, not to the 46, just literally after the log. So this would be x, and then the negative 5 plus 5 would cancel out, and then equals log base 8 of 46 plus 5. So x equals log base 8 of 46 plus 5. We're just going to leave the log there and not find a decimal approximation for it. And then, like I said, that's how the answers will be in your checkpoint as well. Okay, so for b, 10 to the 2x power equals 14. So I'm going to rewrite it down here, just have a little bit more space. So 10 to the 2x equals 14. We have an exponential that we need to cancel out to start to get x by itself. So to cancel out the exponential, we need to make sure it's isolated. There's nothing outside of the exponential, meaning there's nothing multiplied or added out here. So it's isolated. So now we can go ahead and log both sides. So when you have a the base of the exponential is 10. So we would have to log base 10 both sides. But remember, a log with the base of 10 is one of those special logs that we don't usually write the base for. It's just a common log. So we'll just write log of both sides. And there's an assumed 10 that you don't actually write. And then on the other side, we need to do that as well. So that would be log of 14. And then the log with the base of 10 and the exponential with the base of 10 cancel each other out. And it would leave us with just the exponent part of the exponential, so 2x. So this would be 2x, and then equals log of 14. Technically, this one could be used, you could solve it with any calculator, a phone one even, because it's just a common log, but just for the sake of consistency, I'm just going to leave it in that form. And then we want to just get x by itself, so that 2 is being multiplied by the x. I'm going to divide both sides by 2. So 2 divided by 2 would cancel out. X is isolated now, so it'd be x equals log of 14 over 2. And then kind of keep in mind, between the first two problems, I didn't I'm not going to divide these. You can't because it's not just 14, it's log of 14. And then I didn't like add these two together because again, it's not just 46, it's log base 8 of 46. So you wouldn't like combine those. Okay, so for B, x equals log of 14 over 2. Okay, and then this is the last problem. So C is 17 times e raised to the negative x power equals 81. Okay, so we have an exponential, even though it has a base of e, that's okay. We just gotta work on isolating it first. So like that 17 is being multiplied by it. I'm gonna start by dividing both sides by 17 to wipe it out. So the 17 divided by 17 cancels out, and then I'm left with just e to the negative x power, and then 81 over 17. It can't be like reduced or anything, so I'm just going to leave it as is, 81 over 17. And then my goal here is to solve for x, so I would have to cancel out the exponential. In order to cancel out the exponential, I have to figure out the base, and then pick a log that has the same base. So e, remember, was that like random number 2.718 and so on. But there's a special log that has a base of e, and it's called a natural log, and that was like the ln. So we would natural log both sides of the equation, because a natural log, like if I were to do like say ln, or like a log with a base of e, is the same thing as ln. So if you have like the natural log of e, say to the x power, the natural log is like a log with a base of e, so that cancels out the exponential with a base of e, always. So natural log, exponential with a base of e, those wipe each other out, and it would leave us with just the exponent part from the exponential, which is negative x, and then equals the natural log of 81 over 17. And then now I just have to get x to be positive, so I'm just going to go ahead and multiply both sides by -1. Because a -1 times a negative x would turn into a positive x. You could also divide by -1 if you preferred it. And then we wouldn't like distribute the -1 in here or anything. We would just put the negative in front of the like ln. So natural log of, or negative natural log of 81 over 17. So x equals negative natural log of 81 over 17.